Let's talk about mass and weight. They're not the same thing, and the difference is important to understand. Sometimes people get confused about the difference, and sometimes people use one word when they mean the other one. Why is this so hard? There are a number of reasons, and here's one. Mass and weight are terms of art. They're words that we may use in ordinary life, but within the context of a particular discipline, like physics, the same word may have a different and very specific definition. A box of crackers, say, might have a label that gives a weight in grams, but in physics, we don't like the idea of weight measured in grams, and that can lead to miscommunication. A second reason for the confusion is that mass versus weight is really a false opposition, as if mass and weight were different things, when they're not different things. One of them is part of the other one, or a result of the first one. So to make things clear, we're going to have to talk about inertia and gravity, and to do that, we're going to do an experiment. And understanding the results of this experiment can get us closer to understanding mass and weight. We have a chunk of steel hanging by a thin thread. A second thread hangs off the bottom of the chunk, and let's say you pull down on the lower thread. Which piece of thread is going to break? The upper thread, the one that's holding up the steel, or the lower thread, the one that you're pulling on? Let's try this out. First you grab the lower thread and pull down slowly, gradually increasing the strength of your pull. Next, you jerk down quickly on the lower thread. What is going on here? Well, it turns out that this experiment tells us something important about how mass behaves in the world. And this gets at the second reason that people get mass and weight confused. There is something that makes mass different, unique among all the things that we measure in physics, and that is that it has two distinct properties, or natures. The gravitational nature of mass and the inertial nature of mass. One of these natures is related to the result of the slow pull, and the other is what we see in the fast pull. So we're going to start by talking about inertia. Inertia is the property of objects to resist changes in motion. Basically, it's what happens when you give something a shove. If you want to get something moving, you have to push or pull on it. If something is moving and you want it to stop, you exert a force in the opposite direction. It doesn't take much of a push to start or stop a mouse, but something bigger or more massive? Well, a speeding truck is harder to stop because the truck has more inertia. It's easy to think of mass as being all about weight or heaviness, but inertia, the hard-to-stop quality of mass, that's a different thing. Look, if you went out to the space station and you tried to measure your weight up there, you'd find that it's basically impossible. But it turns out you can measure your inertia. You can look it up sometime if you're curious how do astronauts weigh themselves. It's interesting. But for now, let's get back to our experiment and see why inertia matters. Jerk the thread and it breaks. Why does the lower thread break? The hand moves, and it's basically using the thread to talk to the mass and say, hey, chunk of mass, accelerate quickly like me. And the mass says, hey, I would love to accelerate quickly like you, but if I want to accelerate, I need to check with Newton's second law, okay? And Newton's second law says, all right, just a minute, let me rearrange myself to see what you need. Okay, if you want to accelerate, you need a force. And if your mass is big, you're going to need a big force. So the mass says to the thread, hey, little Yankee thread, give me a really big force so I can accelerate. And the thread says, you bet, and it tries. But it is not strong enough. The inertial nature of mass is its resistance to acceleration. When we see the m in A equals F over m, what we're seeing is a math description of inertia. A bigger mass in the bottom of that fraction makes the acceleration smaller. When we talk about Newton's second law, we're talking about inertial mass. A cruising car will stop in seconds. The brakes exert force, The acceleration changes the speed until it comes to a stop in pretty short order. But what if you're cruising on a huge ship with a huge mass? Well, once you decide to stop the boat, you can exert backward force, but you'd better be very patient because that enormous inertia forces the acceleration to be very, very, very small. So, because changes in the speed are so tiny, it can take 10 or 15 minutes to bring a ship to a full stop. Inertia is powerful. Let's talk about weight. Weight is the amount of force that gravity exerts on an object. Gravity is the force of mutual attraction exerted between any two objects that have mass. And if we talk about gravity, we need to talk about this guy. Once upon a time in England, there was a guy named Isaac who was not a very good student. And right after he graduated from college, there was an outbreak of plague. I am not making this up. And he had to go home to his family's farm to quarantine. It turned out that studying during lockdown was a really good fit for Isaac because in the following 2 years, all on his own, he invented a ton of physics. He came up with the laws of motion and a bunch of other things, but let's talk about gravity. This is Newton's law of universal gravitation, and we should talk through what it means. Newton's law of universal gravitation is an equation that tells us the force of attraction between any two objects that have mass m. We could be talking about the Earth and the Moon, but we could be talking about two teacups sitting next to each other on a table. The word universal is in there because every mass in the universe attracts every other mass, but some of those forces are very, very tiny. M stands for mass. And both masses matter. If we're talking about the Earth and the Moon, then we put both of their masses in here. R stands for the distance between the two objects, measured center to center. The G is a constant. It's just a number that makes the units come out okay. Big G, the gravitation constant, is a very, very small number. This equation tells us how much the Earth and the Moon pull on each other, but also how hard the Earth's gravity pulls on more nearby objects, like things that are actually on the Earth's surface. Stuff that's on the surface of the Earth is pulled on by the same gravity that pulls on the Moon. Remember, we're talking about weight here. That's the force of gravity. And this equation looks like a pretty messy piece of math to use just to talk about weight, but we'll see shortly how we can simplify it an awful lot. So in order to do that, we have to think about these objects and their relationship to the planet. The first step on the road to a simpler equation is a tiny little rearrangement. Now we can start to fill in some numbers. We'll start here. R is the distance, not to the edge, but to the center. This is about 4,000 miles or 6,400 kilometers. M is the mass of the Earth, and the Earth is very, very, very massive. Remember G? Just a constant, okay? Here's what's going to make the physics on Earth simple for us. Look at these numbers in red. All these things don't change. The mass and the radius of Earth are numbers that are the same for everything that's on the Earth. So for everything on the Earth, we can smush all these numbers into just one number that should stay the same. The radius of the Earth is a big number. The mass of the Earth is a really big number. And remember that G is a wicked small number. And if we do the math, we multiply and we square and we divide, we get this. 10. The force of gravity on any object on Earth's surface is equal to 10 times the mass of the object. Actually, if we're going to be really precise, the number is a little less than 10, but 10 is simple and it's easy to work with. So we've just turned the law of universal gravitation into a simple, easy formula that lets us compute the weight of any object on the surface of the Earth. And that number in front, whether it's 10 or 9.8, gets its own special name, little g. So here's the upshot. The force that gravity exerts on an object in newtons is equal to the mass of the object in kilograms multiplied by a constant, little g, which is about 10 on the Earth, but would be a different number on a planet that had a different radius or mass. And we call that force the weight. Now we're ready to finish up analyzing our experiment. A free body diagram of this system has only two forces in play, the tension force from the upper thread and the downward force of gravity. Now, the steel is just hanging there. It's in equilibrium, and that tells us the total upward force has to be equal to the total downward force. When you start to pull down on the bottom thread, you add a downward tension to the diagram and to the equation. But this unbalances the equation. The only way for the mass to stay in equilibrium is for the upper thread to increase its tensile force to maintain a net force of 0. But as you start to pull harder, the upper tension has to continue to increase. Which thread will fail first? You can see where this is headed. The top thread will always have more strain on it than the bottom thread does, because the bottom thread is being helped by gravity. So the upper tension approaches the threshold of failure until finally it snaps. All of these ideas come together when we talk about free fall. If we combine what we know about gravity and inertia, we'll be able to see something important. Remember that in physics, when we say free fall, what we mean is that there's no air resistance, a situation that my friend Christine calls physics happy land. Let's solve some free fall problems in physics happy land. Now, someone watching this, and maybe it's you, is probably saying right now that it is silly to solve a problem to find the acceleration of a truck in free fall because maybe you already know the acceleration of objects in free fall. Fair enough. But bear with me here, because in these final minutes, we're going to see how we know the acceleration of all objects in free fall, okay? Okay. First thing, as always, is to draw a free body diagram. How strong is this force? The force of gravity is weight. And we now have an equation for weight. W equals mg. Now put numbers into our equation. The truck's mass is 5,000, the value of g is 10, and you can probably multiply by 10 in your head to get the weight of 50,000 newtons. The number which goes into the force diagram. Okay, we're looking for acceleration. How do we get that? Newton's second law. A is net force over mass. There's only one force acting, so net force is easy. The 50,000 newton weight goes on the top of the fraction, and the mass of 5,000 goes on the bottom of the fraction. We do the division and find that the acceleration is 10. And if you've already learned about free fall, you don't find this surprising. But still, hang in there while we ask exactly the same question, but with a different object. We'll just zip through the problem quickly this time. We need a free body diagram, and we'll compute the force of weight, and it's W equals mg, fill in the mass, and g, and we get a half a newton of weight, which we put in the force diagram. Before bringing in Newton's second law, put in the force and the mass, and the acceleration is 10. And now we can finally ask, why? Why is it that a truck and a mouse both fall with the same acceleration? I mean, what kind of sense does that make? Gravity pulls down on the truck with 50,000 newtons, but on the mouse there's only half a newton. The reason that these two things accelerate with the same acceleration is the dual nature of mass. These two weight forces act because of the gravitational nature of mass. But remember the other aspect of mass, its role as inertia. The truck may have more weight, more force acting on it, but it also has more inertia, more resistance to acceleration, and it has exactly the right amount of inertia to balance out its weight. If we look at the equations, we can see how this works. The acceleration of the truck and the acceleration of the mouse are both given by the equation A is F over m, Newton's second law, and in both cases the force is the weight force, which is found with W equals mg. Let's substitute the weight force into Newton's second, giving us this. And those masses are going to cancel, giving us this. A equals g. The acceleration of a falling object is equal to g. And the mass just doesn't matter. Well, as long as there's no air resistance. So, what have we learned? Mass has two natures, inertial and gravitational. Inertia is the resistance to change in motion. Weight means the force of gravity. W equals mg. G is about 10 meters per second squared on Earth. Objects in free fall all have the same acceleration. And the reason they all have the same acceleration is that their gravitational mass, the degree to which they're pulled down toward the Earth, is perfectly balanced out by their inertial mass, the degree to which they resist changes in velocity.